Ladies and gentlemen, it's a real pleasure to welcome you for the Rock Talk webinar about thermodynamic modeling as a tool to understand hydrated cements. My name is Prof. Lothenbach. I work at Empa in Switzerland on the hydration of cements. I assume most of you know the Powers wellneared model, which can be used to determine pore volumes and the volumes of the hydrates. However, this model is limited to Portland cement systems, and no distinction between different kinds of solids can be made. In addition, we cannot obtain any pore solution composition. An advancement to this model is to use thermodynamic modeling to predict the volume of the hydrates and the liquid phase as a function of the degree of hydration. Such a thermodynamic simulation is more flexible. It can predict which solids will form, how much of it. It's applicable to different kinds of cements, not only to Portland cements, and in addition, it can predict the composition of the pore solution. What I want to do here is to present how one could use thermodynamic modeling as a tool to calculate the composition of hydrated cements, and also to show which tools are available to reach these goals and where you could find them, and how for yourself, or if you want to teach them to your students. Thus, I will first present different possible applications of thermodynamic modeling, and in a second step, I will try to explain different tools available. Now, let's start with the hydration of a Portland cement. I plotted here the relative peak intensity observed by XRD during the hydration, and one thing you can see clearly, it is a reaction. We can see a decrease of the amount of anhydrous clinker, for instance, alite or aluminate, and at the same time, we see the occurrence of hydrates, for instance, portlandite or ettringite. In addition, also a lot of CSH will be formed. However, in a hydrating cement, we don't only have cement hydrates or solid phase or clinkers, we also have some pore solution, because basically the cement only starts to react once we add water to it. And we can measure the concentration of the different ions and elements in the pore solution. And I plotted here the respective picture. You can see initially we have relatively high calcium and sulfate concentration here in pink and yellow, which decrease after a few hours at the moment, basically when we have consumed the calcium sulfate, the anhydride and gypsum initially present in the cement to form ettringite. At the same time, you also can see an increase of hydroxide concentration or of the pH. Silicon and aluminium, which are other main oxides in the cement, are always present in very low concentration in the pore solution. These changes in the pore solution also illustrate the processes, the dissolution and the precipitation reaction occurring during the hydration of a cement. We can try to model such a behavior, and basically what we are doing, we have to find a model to describe the change of the anhydrous clinker and the amount of pore solution in an unhydrated cement to a hydrated cement where we will have less clinkers, and in addition some hydrates which start to fill up the pores and start to interconnect different clinkers. And naturally, the clinkers are not perfect circles. I just have made my life a bit easy to represent them that way. To model such to develop such a model, we can use thermodynamic modeling, which can link the chemical composition of the starting material of the alite, belite, aluminate, and ferrite, and of the minor elements or solids present in a cement to the hydrated composition by the usage of a number of different thermodynamic constants, in particular of the solubility product, which is related to the Gibbs free energy, but we also can incorporate the enthalpy and the heat capacity of these elements. All these data are generic data, which means that they are specific for each solids and can be applied in a beaker of water or in a cement or in a geological environment. The second thing we need is a model to describe the reaction of the anhydrous components, for instance, of the clinker, which react relatively slowly. One simple model available in literature is the so-called Parrot Killer model, where we need as input the surface area of our cement, the water to solid ratio, and the cement composition, and are then able to predict the reaction of halite, belite, aluminate, and ferrite as a function of time in a normal Portland cement. The third thing we need is naturally a thermodynamic database, for instance, the cement database, where we have data for the solubility and the enthalpy and the heat capacity of the different solids which we might find in a cement, such as ettringite, CSH, hydrogarnet, or AFM phases such as monosulfate. All these data are based on solubility measurements at different temperature and the careful characterization of the solid phase composition. This was basically the work of many PhD students who worked hard to get this data. If we now combine this kinetic equation with thermodynamic modeling, we can, for instance, predict the composition of the pore solution, as shown here, and compare it to the measured data. And one thing you can see, you have a nice agreement between the measured data and the pore solution and the calculated pore solution composition. And again, you see, we also predict very little silica and aluminium, and mainly calcium and sulfate, and at later ages, alkali and hydroxide in the pore solution. And the other thing, the good agreement between the thermodynamic modeling and the experimental data also confirms that the hydration, in fact, is a dissolution and a precipitation reaction, which takes place via the aqueous phase. We can use the same model also to see what hydrates we form. And I show here an example for cement without calcite. And basically what we predict, this is our input, the decrease of the amount of clinker as a function of time. And based on that, we predict the formation of CSH, of portlandite, of a little bit of hemicarbonate and hydrothalcite. And we predict also the destabilization of gypsum to ettringite. At later ages, when all the gypsum has used up and the aluminate and the ferrite phases continue to react, we then predict a destabilization of ettringite to monosulfate to account for all the additional aluminium which are present in the aluminate and ferrite phases. We can compare this prediction with experimental data. This is an XRD of a Portland cement without limestone between 1 day to 1 year. And in fact, we can see the presence of ettringite and the appearance of monosulfate at later ages. So we have a good agreement between experiments and calculation. This appearance or this destabilization of ettringite to monosulfate is also something you will find in most textbooks, because most of them have been written several years ago when the cements we have used did not contain any limestone yet. However, modern cements tend to contain a few percent of limestone, and I give you here the calculation for Portland cement with 4% of limestone. And in general, the picture is similar. We predict the formation of CSH and Portlandite. However, we predict now, or we predict still, the formation of ettringite, but ettringite remains stable as we have now the opportunity, the possibility to form monocarbonate instead of monosulfate, and this indirectly stabilizes also the ettringite and leads to a higher total volume. And again, we can compare it to the experimental data. We can see here in the Portland cement containing limestone the presence of ettringite and the appearance actually of hemicarbonate, and at later ages of monocarbonate in agreement with the thermodynamic modeling. Now, why is this important? I plotted here the volume of a totally hydrated cement as a function of the limestone content. If we don't have any limestone, we predict, as discussed before, the presence of monosulfate, while ettringite is expected to be absent. If we add a little bit of limestone, we start to destabilize the monosulfate, first to hemicarbonate and later to monocarbonate, and to stabilize more and more ettringite. This stabilization of ettringite leads to an increase of the total volume of the hydrates. And this is important because we can see this increase also mirrored in an increase in compressive strength in mortar samples after 28 days and 91 days. So we can find, in many cases, a direct link between the calculated volume of the hydrates and the compressive strength. Naturally, it's a bit more complicated than that, but if we stay within one system, we normally find a nice correlation. We can even heighten this effect if we add more aluminium to the mix, for instance, by using an aluminium-rich SCM such as fly ash or metakaolin. And I show here an example on the effect of limestone for Portland cement and for Portland cement plus fly ash. And we can see in the cement containing fly ash, we can see a stronger increase of strength if we have some limestone present. And we also can reach a similar picture if we use calcite clay and limestone as on each, for instance, for the LC3 cement. We can, as we did for the calcite, we also can use thermodynamic modeling to predict the effect of fly ash. I have here blended the Portland cement with up to 50% of fly ash, and we can see if we add more and more, or if we replace more and more of the Portland cement by fly ash, we first predict the decrease of the amount of Portlandite. We predict the transformation of a high calcium CSH to a low calcium CSH, and in addition, we predict the formation of more AFM phases due to the presence of aluminium in the fly ash. And we also can compare that to experimental data. If we concentrate here on the Portland cement plotted at the bottom with the Portland cement fly ash and limestone mixture plotted at the top, we can see in fact much more AFM phases in this mixture, monocarbonate in the presence of limestone, and we also could see the presence of less Portlandite. Now I've shown you different binary mixes, but naturally we also can calculate ternary mixes and plot everything then in ternary diagrams, as I've done here for limestone, Portland cement, fly ash mixing. This is a convenient way to get an overview, to identify where we have maximum and minimum regions. For instance, we can see we have a volume maximum or the same volume as a pure Portland cement in this region, so basically between 2 to 10% of limestone and up to 30% of fly ash. So we can expect that in this composition region, we don't have a strong strength decrease at later ages. We also can use it to study where we would still expect the formation of Portlandite, not surprisingly, mainly in the Portland cement rich area, where we would expect more or less CSH, and where we would form most ettringite or strettlingite. There's a lot of details you can see in these plots, but often you have a bit too much information to digest them all. I want to shortly summarize my Portland cement fly ash limestone findings. We can have a volume maximum, also a strength maximum, if we mix Portland cement with some limestone and fly ash or metakaolin, and we can obtain a high compressive strength, in particular at a bit later ages. If we do that, we obtain less Portlandite, more CSH in the FM phases. In addition, calcite has been observed to accelerate the slag and the clinker reaction. Thermodynamic modeling is very easy to apply for long-term hydration, or alternatively, we must know the kinetics of the reaction, which we can either obtain from experiments, from equation we found in the literature, or from other studies. Unfortunately, we are not yet able to predict the kinetics, or to really predict the kinetics of the hydrates, but I assume in a few years we will also be able to do that. Another topic where we can use thermodynamic modeling to understand our experiments is durability. And I show you here an example of a carbonation reaction. On the left-hand side, I have plotted a hydrated cement with some unreacted clinker, CSH, ettringite, Portlandite, and a little bit of hydrotalcite and monocarbonate. If we add some CO2 to this system, basically to mimic the ingress of CO2 in a hydrated cement, then we generally predict the following sequence. First, we would destabilize any monosulfate or friedel salt present to monocarbonate. Then we would start to destabilize Portlandite, later high calcium CSH to low calcium CSH, monocarbonate to strettlingite, and at very high amounts of CO2 ingress, we also would start to predict a destabilization of ettringite and of CSH to silica fume, aluminium hydroxide, and gypsum. We can not only predict the volume and the kind of hydrates, we also can predict, for instance, the pore solution pH, and we can see how the pH will decrease in several steps depending on which solid phases dominate the cement. Or we also can predict the decrease of the calcium to silica ratio in the CSH from a high calcium silica in the presence of Portlandite to a very low calcium to silica CSH near the carbonation front. In the next step, naturally, we should compare the model with the experimental data. I want to concentrate here first on the Portland cement, which has been subjected to carbonation for at least 28 days. And if we look first in the not carbonated region here marked by the pink color, we can see here in the TGA the presence of ettringite and of Portlandite. If we look on the carbonated region near the surface, we can see the presence of calcium carbonate while the amount of portlandite has decreased strongly, as well as the amount of ettringite or airframe phases. We can do similar observation if we look on a metakaolin limestone blend. Again, we see in the not carbonated region the presence of a tiny amount of portlandite and some ettringite, while in the carbonated region, which is much bigger in the metakaolin blend, we see the presence of calcium carbonate, the disappearance of portlandite, and also the disappearance of ettringite. I want now to present you an overview of the different tools available to calculate the phase composition and the volumes. Basically, there are three main possibilities you can use and teach to your students. You can either use thermodynamic modeling using GEMS or FreakC. You can use a simplified modeling approach based on NanoSEM's SEMGEMS app, or you can use Tenory compatibility diagrams, which as documented in this book chapter in a practical guide to macrostructural analysis of cementitious materials. I want to give you a short overview about each of them. If we start with full thermodynamic modeling, then we basically solve a large amount of equation. I might want to illustrate it here on gypsum, which I have put into a beaker of water. If I do that, then a part of the gypsum starts to dissolve until equilibrium with the solution is reached, which we can describe by the so-called solubility product. In addition to calcium 2+ and sulfate, we also form a number of complexes, for instance, the uncharged calcium sulfate complex, hydroxide or protons are also present, and we can describe all this reaction with some additional complex formation constants, and we have to solve for this system with gypsum and water basically 4 equations. If we would go to a 7th system, then the number of equations will increase very much, and it easily can be 100 equations we would need to solve. So normally we don't do that in an Excel sheet, but we use dedicated thermodynamic codes. One of them is the GEMS code, the Gibbs free energy minimization code I normally use. You also can use FreakC or MinterQ, or there's also a number of commercial products available which you could use. The take-home message I want to give is it doesn't matter which software you use, you will get comparable results. The main differences is in the database which you use or which is associated with the different softwares. The advantages of such a thermodynamic modeling approach is you have the big freedom. You can calculate solid or pore solution composition. You can calculate over or under saturation based on your experimental data. You can calculate the heat generated to compare it to calorimetric data. You can calculate temperature increase. You can use it to calculate kinetics. You have a full access to the thermodynamic data. You can add further solids. You can expand it to any inorganic system you can think of. You can apply to different temperature and pressure. You even have a number of predefined thermodynamic data set, one for cements, the so-called SEM database. There are also databases available for phosphates, for zeolites, and many more inorganic minerals. The disadvantage, it's an expert system. Thus, you need a basic understanding of thermodynamics, the condition under which phases may form or do not form. You might even need some programming skills for advanced problems, and you have to invest an initial learning effort to be able to handle the software. However, there's also a collection of a complete course in videos and tutorials available on our homepage. We regularly update them when we have a new course, and we also offer at least every 2 years a course for PhD students on how to learn the software. And the videos are available both in English and Chinese under the following web page. A second option to do thermodynamic modeling is to use the newly developed SEMGEMS app, which you can find under this address. It has been developed by Dimitri Kulik and the team around him and financed by NanoSem. A paper describing the main application is about to be submitted to the Rilem technical letters. You will soon find it there. And in addition, a hands-on training online course is planned for this month. You just have to register this week in SEMGEMS to get an invitation. The use of the SEMGEMS app, even without this course, is quite simple. You have to register, you have to select a cement recipe from a template, which uses either XRF or the mineralogical composition. You have to equilibrate it. You also can adapt the composition or select some supplementary cementitious materials. And then you can select the process, for instance, blending, hydration, ingress of carbonation, and press simulate, and then you get a respective plot. The advantage, it's fast and easy to use. You can use it anywhere as it's web-based. You get as output solids and pore solution, heat generated. There's a number of predefined processes available. And you also can calculate the temperature increase. The full complexity of GEMS is also captured in this web tool. On the disadvantage, it's still very new. So we are still somewhat in a testing stage. We need a bit more user feedback, and we don't have direct access to thermodynamic data. Thus, I cannot add additional solids and or change their stability. As a snapshot, I plotted here the effect of limestone picture calculated with GEMS as we've seen before, and on the right-hand side, the same picture calculated based on SEMGEMS, and basically we see the same phases, CSH Portlandite, we see the destabilization of monosulfate to hemium monocarbonate, and the stabilization of aggregate. So basically we get the same or very similar results. And naturally you can make much nicer picture if you export the data to a respective software. The third version you can use is the so-called Tenory compatibility phase diagrams, which have been originally developed by Duncan Herford. This is basically based on the idea that for an existing cement, you can plot the composition of the hydrates on two ternary diagrams, one consisting of calcium oxide, aluminium oxide, silica oxide, and on a second one focusing on C3A, calcium sulfate, and calcium carbonate. And for each cement composition, you will find a unique solution. So for instance, here in red, the Portland cement with no limestone will be placed between the CSH composition, Portlandite composition, and AFT and AFM composition. If we look here on the second diagram, which AFT and AFM phases may have formed, we can see we predict mainly some monosulfate plus a minor amount of aggregate. If we do the same thing now with some limestone, we can see we don't see any change here. However, the point in the second ternary diagram now moves from the monosulfate ettringite system to a heterogate monocarbonate calcite system. And if we add more calcite, then it moves even further. We can get the total amount of the phases formed and use that in whatever application we want to use it afterwards. You can download the Excel sheet for free at empa.ch Tenory. I want now to conclude on the available tools. You have different options: full thermodynamic modeling for experts, a somewhat simplified modeling at the SEMGEMS app, or the use of compatibility diagrams if you just want to know the amount of hydrates. The conclusion on the thermodynamic modeling: it is a very versatile tool. You can predict hydrates, volume, porosity, pore solution, heat under oversaturation. It's applicable for Portland cement, blended cement, calcium aluminate cements, and many more. It's a powerful tool in combination with experiments. It supports interpretation of experimental results. It can help to interpolate in understanding, and there's a number of tutorials available. And for updates, please see empa.ch/semdata. I thank you for your attention and will be happy to answer any of your questions.